Exercise 41.12. The exercise is to be solved with the assistance of the TI-Nspire CX CAS version 3.2. Consider the region bounded by the graphs of y equals to negative x squared plus 6x minus 4, y equals square root of quantity x minus 2 plus 2, and y equals 3 times the square root of quantity 4 minus x plus 1. Part A. Provide a graph of the region. Part B. Provide a graphic approximation of the area of the region. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Part E. If able, obtain an exact value for the area of the region. Part A. Provide a graph of the region. Okay, I think I would like the first page to be a summary of the solution, and so I'll start off by adding a notes page to get started and titling it as Exercise 41.12 Solution Summary. For Part A, we plan to put the graph of the region on page 2, so I'll mention that right here. Now, another thing is I would like this title to be bold and prominent, so I think I'm go back here and format the text so that it is bold, and I think we can get a larger font to fit there. Okay, and maybe centering it a bit like so. Okay, now on to page 2. Start the graphing of the region. So for that it's Control Add Page and a Graphs application. The entry line is already open, and let's look at the bounding graphs here and see what we have. The first one, the y equals to negative x squared plus 6x minus 4. Always a good idea to try to anticipate what the shape of the graph will be even before the Nspire provides a result. It's kind of just good practice for you, because one of those central math skills is to be able to just look at an equation and visualize very much what the shape of the graph will be. In this case, what are we expecting? Okay, that's a quadratic function with a negative x squared term. That means we expect to see a parabola opening down. It'll be a translation of y equals to negative x squared, and we even know that the x-coordinate of the vertex will be the opposite of b over 2a, or negative 6 over 2 by negative 1, which would be 3 in this case. So all that can go on in our minds before we start, and otherwise we can keyboard it on in here. Okay, as we expected there, let's push tab, bring up the entry line again, and let's see what we have coming up next here. The second equation, a y equals to the square root of x minus 2 plus 2. What comes to mind there? Okay, well, we have mentioned before that y equals to a square root of a linear expression in x is always a semi-parabola. So this will be a semi-parabola. The plus 2 will translate it up to units. And the x-coordinate of the vertex, solved from radicand equals 0, something else that could be done mentally here, that would be x minus 2 equals 0. That's x equals 2. Okay, so we have all that going in our minds before we keyboard this in. Otherwise, let's proceed. Okay, as we were expecting. Another reason you want to really be sure you already know what these shapes are is that you want to also be able to decide whether or not there are bounded regions outside of the screen that is lying before you. How will you know that? Do the curves turn around and re-intersect some more? Unless you are confident of the shape of the graph, you will be always wondering that kind of thing. Okay, on to the third one here. Y equals to 3 times square root of 4 minus x plus 1. Okay, Once again, this is a y equals to square root of linear expression in x situation. This will be a semi-parabola, and the x-coordinate of the vertex will be, from solving 4 minus x equals 0, gives us x equals to 4, and the axis of symmetry is horizontal, and that 3 factor there tends to produce some vertical stretch, right, in the world of transformation. Okay, let's keyboard this in and see if this is indeed the case. Okay, so based on what we can sort of see here through all the labeling is a rather small enclosed region. But since we know that the red graph and the black graphs are both semi-parabolas, we know there is nothing else to expect other than this as the enclosed region. So we want to make this very big and prominent in our graph to make our graph high quality. And so to start that here, I think I'll use a zoom box. So we go to a menu and Windows Zoom, Zoom Box. First corner. Alright, I really like to have the axes appear in my graphs if I can. And here I think I still can get them to appear while still providing a pretty good sized enclosed region. So I'll put one corner here and then come out to where I just sort of capture the enclosed region. I want to make sure we have room for labeling as well. Try that. Okay. Let's see. I think I will accept this for the starting point. Push escape to put away that tool. And next thing I might decide to do is perhaps clean up these axes a bit here. I see they're very densely scaled, and these end numbers 5.28, 4.65, maybe something a little simpler there as well. So up to the menu, and in the Windows Zoom, we go to the Windows Settings. Okay, X-Min, since I want to retain the y-axis, I make at least something somewhat negative here. How about negative 0.5, tab X-Max, okay, 4.5, say. Scaling one apiece. Y-min. Okay, at least something slightly negative to retain the x-axis in view, and a sort of round number or a simple fraction like negative 1/2. Alright, and here a max of, okay, I'll make that 5.5. And scale every 1 unit per tick mark. How's that look? Okay, I think quite a bit cleaner. Alright, let's see. Let me start moving these graph equations around so that they're not getting in the way of things. Okay, maybe about like so. Now another piece of important information that surely belongs on the graph, and that would be the points of intersection. Before I proceed further, I would like to make sure that I don't have huge number of digits on this coordinates. That would make my graph look rather cluttered. And since the area here looks like a rather small number, I think just 2 digits would be fine here. So to get that arranged, I go to Menu and go to the Settings. So here's the Graphs and Geometry settings. Let's decide to float 2 and go with OK there. Now I'll go ahead and proceed to get these intersection points. For that, we can go to Menu and Geometry, Points and Lines, Intersection Points. Okay, to use this tool, you pick your 2 graphs and it provides the intersection points from there on. So let's go with F1, click to select it, graph F3, click to select. There's an intersection point. Let's see, right now I don't think no, I have to close the tool off to move the coordinates around. So let me just continue getting the other intersection points. let's pick graph 2 and graph 3. Okay, that point there. And we'll need to get graph 1 and graph 2's intersection, that point there. Alright, now I can put away the tool with the escape key and make this look more orderly. Okay, now let's see. We want the enclosed region to look very prominent, so it's time to shade it. How about doing that? Well, let's see. One nice way is to outline it with a polygon and shade the polygon, and then erase the polygon, leaving behind just the shading. Also, the polygon will serve as a great device to provide a graphic approximation. Okay, so for that, menu, geometry, shapes, polygon. Alright, find a point and click. Okay, put away the tool, got the polygon there. And let's see, let me select the polygon and context menu, go for some coloring, a fill color. How about yellow? Alright. Now I do want to clean this up further. However, this polygon that I'm using as a shading device is also useful to me for part B of this question. So I am going to keep a copy of this to let it proceed to be a part B answer, and then let this go on to become cleaned up as a graph of the region. So to do that, I'll go here with Control, Show Document Pages, and now it's a matter of going here, Context Menu, Copy, Context Menu, Paste. There we are. Now returning to page 2 to clean this up further. Alright, the lines segments of that polygon, that's distracting, so context menu, let's color those yellow as well. So line color, pick yellow. Okay, looking better. One more thing, those vertices, except for the ones that happen to also be intersection points, are distracting, so we can get rid of those by going to the point, context menu, hide, and just do that continuously. Alright, one last remaining item here, and that is the person looking at this graph. I want them to certainly know what is going on here, and that is that the bounded region is shaded yellow. So I'll just put that in some text here. Okay, I suppose that's a pretty complete graph for the part A there. Got all of the boundary lines with their equations labeled, key intersection points with approximate coordinates, and the boundary region itself is shaded and labeled, and the axes are scaled and labeled as well. Okay, great. Part B, provide a graphic approximation of the area of the region. Alright, got this polygon. Now I want to use it as a source of graphic approximation of the area of the region. So to do that, select it, context menu, measurement, area. Okay, got this here. About 1.5 square units. Actually, to make a sort of complete sentence on that, I think I will come out here and put on a little bit of text. Okay, and now I'd like to return to the notes page to keep the summary going here. So now we have a 1.5 square unit statement to make for part B. Alright, there we are. Great. Part C, provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. For a calculus calculation of area, One strategy begins by slicing up the region. Here in rectangular coordinates, the kind of slicing is a matter of two choices: thin vertical rectangles or thin horizontal rectangles. Thin vertical rectangles is by far the most popular. Let's try that first right now. Let's examine for how many different types of rectangles have resulted. As far as the tops of the rectangles go, it's always the same. Top is always defined by the blue F1 graph. As for the bottoms of the rectangles, okay, little change. They start off being defined by the black F3 graph. Then they change to be defined by the red F2 graph. Okay, two types of rectangles. That's not too bad. So let's decide to stay with this strategy, and that means we'll need to informally formulate the area of two types of rectangles. A rectangle area is always length by width. For the rectangles on the left-hand side of the region, their length is determined by upper y minus lower y, or what becomes f1 of x minus f3 of x. Their width is dx. As far as the rectangles on the right side of the region, their length is an upper y minus lower y, which becomes f1 of x minus f2 of x, times their width of a dx. Okay, it's time to implement that strategy that we have developed visually on the Nspire. And here on the summary page, I want to give the person reading this document a brief summary about our strategy. Okay, so as we have mentioned here, we are going to be storing our limits of integration into variables a1a, b1a, c1a. Okay, we have to actually do that now, so let's go back to the graph of the region and take care of that. Okay, here is our A1A. The traditional labeling of limits of integration is A for the smallest, B for the next, and C, and so on. Okay, so here, context menu, store, and the variable A1, the one because we don't want to just use single letters to define variables on the Nspire, and then another A because this is only a decimal approximation of the limit of integration. And reminder, those two digits we see here, that's not what the Nspire is going to be using in its calculation. Those are just the displayed digits, two displayed digits. Internally, the Nspire is holding on to something like 14 digits of precision for that number. So no need to worry about that. And enter. And next one here is here, right here. Let's go to store. And this will be the B1A. Enter. Here we are. Store. C1A. Okay, got those stored away. Back to the notes page where we can complete our calculation. Now let's go to the menu, calculations, calculus, integral. Okay, that first integral going from A1A tab to B1A tab. Looking back at our graph of the region, we remind ourselves that the thin vertical rectangles here are of length f1 of x minus f3 of x. Tab and dx is the width of those little rectangles. Okay, forward arrow and a plus. Back to the menu, getting the second integral set up here. As before, calculation, calculus, integral. Okay, this one going from B1A, tab, C1A, tab. Alright, back to our visualization there. We had, for the lengths of these rectangles, f1 of x minus f2 of x. And their width is a dx. Okay, enter. Alright, very nice. Now wait a minute. One thing offhand, and that's that this question asks for 5 significant digits. There are 6 there, too many. Hold on, let's go back here for a minute, and let's go to document and settings and document settings, and let's make this a float 5. Okay, there, it fixed it right up, and now we have the 1.5647. Another thing to make this read more cleanly, that little triangle there, I'd like to make that into an approximately equals to sign. So here for the math box attributes, let's make the insert symbol an approximately equals to sign. Okay, there. And maybe the last thing, to tack on the square units. A little nice extra to put on here. Okay, so there is our part C. The crucial part D is what we're really looking forward to checking out right now. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Okay, to assess the correctness, let's go back and look at that graphic approximation and then re-record it here. Okay, that was 1.5 square units. The calculus solution is still there before us. Okay, so what do we think here? This looks actually quite good, right? 1.5 as comparing to 1.5647. All right, now let's see the larger number. If we took 10%, that'd be about 0.16. Okay, and how much difference have we got here? We have about 0.06, kind of a difference, 0.065. And so if we were to talk about what is 5%, that'd be about 0.08. So it's no exaggeration to say these two results are within 5% of each other and thus consistent. Therefore, we believe that the solutions to part A and B are likely correct. Okay, great. Part E. If able, obtain an exact value for the area of the region. Okay, an exact calculation requires us to pass 2 stages of calculation. One is getting exact limits of integration, and 2 is then following that up with exact integral evaluations. Okay, got to start with those limits of integration. Let's tell the person reading our document our plan here. And as far as the details of this work, let's move the details on to another page, page 4 of our document. Okay, and let's go ahead and, alright, first go to page 3 and then Control Add Page. And this will be a calculator page. Alright, so solving, say, the F1, F3 intersection, which was our A1A, would give us our first limit of integration exactly. Ooh, wait. A decimal approximation, not an exact solution. What to think about that? Let's check our calculation mode. So let's see here. Document. Settings and status, document settings, calculation mode is in auto. Okay. Auto means if you put in inputs that do not have decimal point numbers, the Nspire will indeed provide exact if it finds the exact result to be something concise. So, this is not going to improve by changing the calculation mode. By the way, if you move this to exact, things only get worse. You end up getting the equation handed back to you, just shuffled around a little bit. You won't even get a decimal approximation. So auto is a perfectly good mode for us here in this case, as we did not input any decimal point numbers. This means we are not going to be able to provide an exact solution, since we could not find A1 exactly. We can go back to the notes page and record that. Okay, that actually answers the question asked in part E. Now we might like to go a little further here and kind of think about this. Why is it an exact value was not obtained, considering that this is exercise 12, and if you have worked on the preceding exercises here, and that would be 2, 4, 6, 8, 10, we have to this point always succeeded in getting exact values all the time. So let's maybe explore a little bit about what equation the Nspire had to deal with, and were there exact values even possible, and if so, why did it find them to not be concise? Okay, we can explore that next. Part E Addendum, determining why the Nspire did not provide an exact solution when solving the equation f1 of x equals f3 of x. Let's begin by trying to determine what type of equation the Nspire's computer algebra system encountered when it abandoned trying to provide an exact solution. A computer algebra system, much like us humans, likes to have equations in certain formats so that it can apply certain well-known algorithms to solving. In the case of the f1 of x equals f3 of x, it probably noted it was a radical equation and tried to eliminate the radical so that it would obtain a polynomial equation and then pass off the equation to its special polynomial solving subprogram. So let's try to retrace the Nspire steps. Okay, I think I would first like to explain to the person reading this document what I'm doing next here, and so I want to put a little bit of text in. How can you put text into a calculator application? You can do something like this. Go to the menu, Actions, and Insert Comment. Okay, so now we can explain here that we are exploring the reason for not getting an exact solution. All right, and to begin, maybe take a look at what was f1 of x, the left-hand side of the equation. Okay, yeah, that was that quadratic expression. And what about the f3 of x? All right, that had the radical. So now, if we imagine having that f1 of x equals f3 of x, we see the radical equation, and the Nspire's computer algebra system is going to proceed just as we would manually at this point, and that would be to isolate a radical, and then to, square both sides to eliminate the radical. All right, so what would that entail here? Well, the f3 of x expression has 3 times radical 4 minus x, and there's that plus 1. Okay, so we would be subtracting 1 from both sides and then squaring both sides. All right, well, let's sort of work out that right here on the Nspire. And what we can do is we can go to the menu and go to the algebra and call it the expand. And for expanding, I'll put a parenthesis, go up here, grab f1 of x, subtract 1 from it, forward arrow to escape those first set of parentheses, and now I'll square that. Alright, so there would be the left hand side, subtract the 1 and then square it. What does that look like? Okay, we get that. Now, what about the right hand side? After we squared both sides, we can do the same thing there. I'll go to the menu, under the algebra, expand, and for this expansion we can go up here and grab f3 of x. Want a parenthesis in front of it because we plan to make a f3 of x minus 1. Escape those parentheses and now square this. See what the result is. Okay, that would be the right hand side of the equation after that step. Alright, now let's put together the entire new equation so that and make it equal to 0. We'd be doing that next if we were working manually. So I'll go here, select this, paste this on the new line. I will now subtract in parentheses. Just go up here and grab this, select it, enter, paste it there, and then if we just enter, it will perform this polynomial subtraction for us. Okay, sitting there is the left-hand side of the equation the Nspire's got to solve after it takes care of the eliminate the radical stage. What about that? It's a fourth degree or quartic equation. Now, we actually happen to know about these. The question is there an exact solution to every quartic equation? And this is actually a pretty well-known result. We have the result that yes, indeed, there is a quartic formula. Just as we have a quadratic formula that solves any quadratic equation in terms of radicals, there is a cubic formula that solves a general cubic equation. However, it's kind of interesting to find that for the quintic equation or fifth degree equation, no general formula in terms of radicals exists. So the second degree, third degree, fourth degree polynomial equations all have exact solutions available. From the fifth degree on, no, you're not assured of that any longer. Kind of interesting result of algebra. So now that we've found that the Nspire's computer algebra system has probably encountered a quartic equation along the way, and we know that the quartic equation has a quartic formula which provides exact solutions, we are wondering why the Nspire does not provide exact solutions. Well, looks like it's time to explore the quartic formula. To put the quartic formula in context, let's briefly review the quadratic formula. The quadratic formula is actually the conclusion of a theorem that begins by saying if you have a quadratic equation written like this, and here we see our familiar format, ax squared plus bx plus c equals 0, then, and here's the well-known quadratic formula. There are two solutions or roots, and since they are square root conjugates, they are nearly always written in this compact form using a plus or minus symbol. We could give each one of the two roots its own formulation, and then the quadratic formula would appear like this. Okay, nice looking and pretty simple. Both formulations easily fit on a single screen. No need to scroll right in order to show the quadratic formula. It's short and sweet. Okay, let's discuss the quartic formula. Just like the quadratic formula, the quartic formula is a conclusion to a theorem that begins by saying if you have a quartic equation written like this, and this may not look general at first because there's only one x to the fourth, But if you think about it, no matter what you have for your quartic expression, you could divide both sides of the equation by the x to the fourth coefficient and rewrite it like this. So this represents the general case. Now we have the then part, and we have our formulations for the 4 roots or solutions. Are you ready for this? Here we go. Wow, those quartic equation solutions can really be complicated. And the Nspire, after all, has a policy where it only records exact solutions when it deems them concise. So it looks like what happened here is that the Nspire determined that the exact solution to the f1 of x equals f3 of x equation was not concise and resorted to a decimal approximation at that point. Okay, nice thorough treatment of exercise 41.12. Good job.